Many different partitioning methods are available. Fundamentally, they all work similarly. First, the data analyst decides on the number of market segments to be extracted. The partitioning algorithm then randomly selects as many consumers from the dataset as segments will be extracted. These consumers are declared segment representatives. Next, one consumer is randomly chosen. For this consumer, the distance to all segment representatives is computed. The consumer is assigned to the segment representative closest to them. Then the next consumer is randomly chosen, and the same process is used to assign them. And the next consumer, and the next consumer. Once all consumers have been assigned, the partitioning algorithm checks if the initial segment representatives are actually good representatives. Good representatives have a small average distance to their segment members. For segments where this is not the case, new, better segment representatives are chosen. Then the process of assigning each consumer begins again. And it will do so until the point is reached where better segment representatives cannot be found anymore. The most commonly used partitioning method is k-means. It pretty much follows the generic process that we just discussed. It minimizes the sum of distances between each consumer and their closest segment representative. The performance of k-means can be improved by choosing good starting points. Starting points are the consumers chosen randomly at the start, the initial segment representatives. Because they are chosen randomly, they are unlikely to be good representatives. You can see an example of a bad starting solution in this figure. Segment representatives are shown as stars, and consumers are shown as dots. You can see that 3 segment representatives are very close to one another. As a consequence, the 4th representative covers a vast area, including consumers who are very far away. This is a better set of starting points. The starting points are nicely distributed across the space and capture consumers who are close to them. But how can we ensure that our starting points are good? An easy way to achieve this is to draw many sets of starting points, say 100. For each set of starting points, we run k-means and choose the best solution. This is what improved k-means does. Another partitioning method is hard competitive learning, also known as learning vector quantization. K-means adjusts the location of all segment representatives after all consumers have been assigned to their closest segment representative. Hard competitive learning does not wait until all consumers are assigned. Rather, it moves the segment representative closest to a consumer towards the consumer immediately. Because of this difference, results can differ from those obtained by k-means. Hard competitive learning is not better or worse than k-means, it's just different. Another variation of hard competitive learning is neural gas. Neural gas moves both the closest and the second closest segment representative towards the consumer at every step. Topology representing networks additionally count how often representatives get updated together. They use this information to create a map of segment representatives. The map shows the proximity of segments to one another. Self-organizing maps, or self-organizing feature maps, take the idea of topology representing networks a step further and allow an even larger set of segment representatives to update at every step. At the start of the process, the extent of change is large, and then it continuously decreases. Also, self-organizing maps impose a grid on segments. As a consequence, self-organizing maps produce good maps of segment proximity, but can come at the cost of a higher sum of distances between consumers and the best segment representatives. As you can see in the map here, each circle is one segment, adjacent segments are similar to one another, and the pie chart inside the circle describes the nature of the market segment it represents. Whichever partitioning algorithm we choose, it's important to understand that they're all based on distance calculations. It's therefore important to choose the underlying distance measure wisely. Have a look at this picture. You can see 3 different segmentation solutions, derived from the exact same dataset with the k-means algorithm. The only difference is that Euclidean distance generated the solution in the far left plot, Manhattan distance produced the solution in the middle plot, and angle distance led to the solution shown in the right plot.